Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Material Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. Now let's just get started on our set of questions for today's session. Okay, so question 1 says to explain the electron configuration of copper. Okay, so first let's write out the electron configuration for copper. And the first step in writing the electron configuration is to first divide your periodic table into the different orbital shells. So here's an example of the periodic table and how it is divided into the S block, which are the first two columns here, and the P block, which is this green section. The D block are the middle transition metals, and the F block are these last two rows, which are the lactanides and actinides. So we identify copper on the periodic table, so you can see it's right here, atomic number 29 in the 3D section. And then starting from hydrogen, we move left to right across the periodic table, writing the row number followed by the block letter. And also in superscripts, we're going to show how many electrons are in that orbital. So let's start off writing the electron configuration. So starting from hydrogen, we write the row number 1, the block letter S, and then to show how many electrons are in this orbital, we use the superscript of 2, since only 2 electrons can fit in the S orbital. So now we're on to the next row. So row 2, block S, and again, 2 electrons will fill this orbital. And now we move over to the 2p section. And in the p orbital, this can house 6 electrons. So we write 2p6. And then to the next row, we write 3s, 2. And then moving over, we write 3p6. And then we move over to the next row, which is 4s, and then 2. And then finally, when we get to the D block, you'll notice that we write the row number minus 1. And similarly, when we get to the F block, we write the row number minus 2. So when we get to the D block, we write 3, and then D, and then count up all the electrons up to copper. So we count out 1, 2, 3, 4, 5, 6, 7, 8, 9, and we write 3D9. Okay, so here we have the initial electron configuration for copper. That's a 9. But typically, the 3D orbital becomes lower in energy than the 4s orbital when we have transition metals. And it's more likely that we are going to fill in this d orbital than we are to fill in the 4s orbital. So I'm just going to add a note here that for transition metals, the 3d orbital becomes lower in energy than 4s. So what we do now is we kind of give one of the electrons from the 4s orbital to 3d, and we switch the two to write an increasing energy. So let me just write what we have so far. And now we can write 3d10, so it will be in lower energy than 4s, and also one of the electrons in 4s will move into the 3d and fill that in first, so that we have a filled d orbital. And then to show we have one more electron, we just say 4s1. So now this is the final electron configuration for copper. So now let's see what the junior tutor said. In writing the electron configuration of an element, we follow the off-bow principle, shown below, which states that the order of energy will dictate the order in which electrons are arranged in its orbitals. Therefore, the lowest energy will be occupied by electrons first. Remember that each orbital can hold a different number of electrons. The s orbital can hold 2, the p orbital can hold 6, the d orbital can hold 10, and the f orbital can hold up to 14. So copper has 29 electrons, and using the off-bow principle, the electron configuration is the following. So this is what we had initially as well. However, for transition metals, the 3d orbital becomes lower in energy than the 4s orbital. Thus, the correct electron configuration for copper is the following. So it ends off with 3d10 and then 4s1. Yep, so this solution is correct. Okay, so question number 2. A glass that holds 0.5 liters will hold how many milliliters? Okay, so first let's bring up the conversion factor from liters to milliliters. So 1 liter is the same as saying 1,000 milliliters. So this is our conversion factor. So if we have a glass that holds 0.5 liters, to convert it to milliliters, we need to multiply by this conversion factor. So our desired units will always be in the numerator, because our end goal is to cancel out our undesired units, which is the liters. So for example, if the liters was in the denominator instead, then we would multiply with the liters in the numerator if we wanted to get rid of it. But since liters is our main unit, we would multiply by 1,000 milliliters over 1 liter. So this is the same thing as dividing 1,000 by 2. So now our liters will cancel out, and we're left with our milliliters, which is 500. Okay, so now let's see what the junior tutor said. 1 liter is equivalent to 1,000 milliliters. Using this conversion factor, 0.5 liters times 1,000 over 1 liter equals 500 mils. So a glass that holds 0.5 liters will hold 500 milliliters. Okay, so this solution is correct. Okay, so question 3 is, what is the IUPAC name for the following compound? So let's also draw this compound down here. So this is an organic compound. and specifically, it contains mainly hydrocarbons or only hydrocarbons. So this means it only contains carbons and hydrogens. Okay, so it looks kind of like this. And when naming these types of compounds, the first step is to find our parent chain. And to find your parent chain, we basically want the longest chain with the most important groups. So typically when we have an organic compound, sometimes there are other functional groups such as alcohol groups or double bonds, triple bonds. And this is what I mean by most important groups, like those functional groups. But for our example, we only have a chain of carbon and hydrogens, so we're only looking for the longest chain in this case. So a common mistake I see people make is they just think that the longest chain is the one that is like horizontal like this, like the easiest one to circle. But if we counted out how many carbons are in this chain, you only have 5 carbons. So this isn't the longest chain that we could form with this compound. The longest chain, in fact, involves these carbons as well. And then we kind of want to circle it so that we can visualize the chain. And then when choosing to go up or to the side or down, notice that if we go down, this is also the longest chain as well. Okay, so here I have circled the parent chain, which is the longest chain with the most important group. So in this case, it's just the carbons. So the second step is to number our carbon chain. And in the end, we want the lowest number possible when designating where all the side groups are. So I'm also going to add a step 3. This will help us number the carbon chain. Step 3 is to identify our side groups. So these two steps can kind of be merged into one, because if I identify my side groups, I'll see that I have 2 methyls here and another methyl here. So every time we have just 1 carbon with 3 hydrogens as a side group, this is called a methyl side group. And when I want to number the carbon chain, I mentioned earlier I want the lowest number in my final answer. So notice that if I can either start numbering from here and make this 1, 2, 3, 4, 5, 6, 7, 8, or I can start numbering from the bottom and number this as carbon 1, 2, and then 3. So notice that 2 of my methyl groups are on carbon 3 if I started counting from the bottom, but if I started counting from the top, this would be carbon 6. So therefore, if I start counting from the bottom, and this is now carbon 3, then in the end, when I name my compound, I'll have the lowest number possible. So therefore, I know I need to start numbering from the bottom there. Okay, so that was step 2 and 3. And now step 4 is to finally name our compound. So we want to name our substituents first. So in this case, these are the methyl groups, and I have 3 methyl groups in total. So to show which carbons my methyl groups are on, this is where I would number. On carbon 3, I have a methyl, and also on carbon 3, I have another methyl. So I have to write 3 twice to show I have 2 methyls there. And also on carbon 5, I have another methyl group. So I write 3, 3, 5. And then to show that these carbons contain my methyl groups, I put tri-methyl. Since we use the prefix tri to tell us that there are 3 of it. So 3, 3, 5, trimethyl. And then again, our parent chain would be named last. And since our parent chain is 8 carbons long and it only comprises of single bonds, then I know that it is 3,3,5 trimethyl octane. Yep. So this is our final answer. Okay, so the junior tutor said that in naming alkanes, the parent chain corresponds to the longest possible chain of the compound, and the prefix used for the name varies depending on the number of carbon atoms comprising this chain. The table below shows some of the prefixes used in naming alkanes. Note that the prefix is added to ane, which is the characteristic name of an alkane. So alkanes are single bonded carbons. Okay, so they summarize all the different parent you could have and the name of that alkane. So in our case, since we have 8 carbons, this is where the octane came from. After naming the parent chain, assign locants to the chain in such a way that the substituents get the lowest number possible, and then name them. If it is an alkyl group, the prefixes shown in the table also apply. Instead of adding ane, you add il. So here we have the meth, and then since it's a side group, we add il instead of ane. In the case of the given compound, the longest possible chain is composed of 8 carbon atoms. So the name of the parent chain is octane, and the substituents, on the other hand, are alkyls composed of only 1 carbon atom, so their names will be methyl. So they color-coded the parent chain in red and named the compound 3,3,5-trimethyl octane. Okay, so this solution is correct. Okay, so question number 4. Is hydrogen sulfide H2S polar or nonpolar? Okay, so to answer this question, we first need to write the Lewis structure for hydrogen sulfide. So to do that, we need to calculate the total number of valence electrons in this compound. So hydrogen has 1 valence electron, and there are 2 hydrogen atoms, so we multiply this by 2. And the sulfur contains 6 valence electrons. So in total, we have 8 valence electrons for this compound. So now I'm going to draw sulfur as my central atom, since compared to the hydrogen, it is able to form multiple bonds. And then I can draw 2 bonds to hydrogen. Okay, so if we recall that each bond contains 2 bonding electrons, and we have 2 bonds, then I only have 4 out of the 8 electrons drawn in this structure. So I draw the remaining 4 on my central atom like so. Okay, so now we have kind of like this bent structure. And we need to find out the electronegativity difference between the sulfur and the hydrogen. So I'm just going to look up the electronegativity values of all the different elements. Okay, so the electronegativity value for sulfur is 2.58, and for hydrogen, it's 2.20. Okay, so when we find out the electronegativity difference, we only get around 0.38, which isn't that big of a difference. So in fact, when we have an electronegativity difference that is less than 0.4, this makes our bond nonpolar. So there is quite a debate on whether or not this molecule is polar or nonpolar, because we can also look at its bent structure. So because of this bent structure, we just have the tiniest dipole moment going towards the sulfur because it is a bit more electronegative than our hydrogens. And due to the electrons, they don't cancel each other out. So I would say that for this question, H2S is considered slightly polar. Just due to its structure. But mainly nonpolar because the bonds that comprise of this molecule are nonpolar. So if we have nonpolar bonds, then that means we have a nonpolar molecule. So again, it's a bit up for debate. So let's see what the junior tutor said. Polarity is the product of the uneven distribution of electrons among atoms or molecules in a compound. The polarity of the compound depends on the electronegativity of the atoms that make up the compound. In order to determine the polarity of a compound, the electronegativity difference between bonding atoms is calculated. The electronegativity value is less than 0.4, it's considered nonpolar, and if it's between 0.4 and 1.7, it's considered polar. If it's greater than 1.7, it's considered ionic. So they calculated their value to be 0.4. So a lot of different references have various electronegativity values. You can see that for theirs, they got 2.6 for their sulfur instead of the 2.58. So if we looked at a different table that rounds, you'll see that it's 2.5 here. So again, this is why it's up for debate, because if we consider the carbon-hydrogen bond, the carbon-hydrogen bond everyone knows is nonpolar, and it would have the same electronegativity difference as 0.4, which is the same as the hydrogen-sulfur bond. So they said that this was a polar compound, but I'm just going to write in what I know as well. So the explanation for this solution is mainly correct. However, the actual polarity of hydrogen sulfide may be up for debate. Since the sulfur-hydrogen electronegativity difference is the same as carbon-hydrogen, which is considered a non-polar bond. The bent structure of this molecule may lead to a slightly polar molecule. I'll just put it in quotation marks, slightly polar. But I'll still say this solution is correct since they gave some valid points. Okay, so question number 5 is, what is the molar mass of sodium bicarbonate, NaHCO3? So to solve for the molar mass of sodium bicarbonate, we need to know all the different individual atomic masses of the atoms involved, and we can find these values using the periodic table. So for the molar mass of this compound, it's going to be the molar mass of sodium plus the molar mass of hydrogen plus the molar mass of carbon plus 3 times the molar mass of oxygen, since we have 3 oxygen atoms in this compound. Okay, so again, we use the periodic table to find these molar mass values. So for sodium, it's 22.99 grams per mole. Hydrogen's is around 1.01 grams per mole. Carbon's is 12.01 grams per mole. And oxygen's is around 16. So if we add these values together, we get a total molar mass of 84.01 grams per mole. And the junior tutor said that molar mass is often expressed as grams per mole and refers to the mass of a substance when 1 mole of it is present. Numerically, this is often equated to the formula weight, which is equal to the sum of the atomic weights of all the atom constituents. Hence, to solve for the molar mass of each compound, we just have to add the atomic weights of each atom in the compound. And they also got around 84. So this solution is correct. Okay, so question number 6 says to talk about the SN1 reaction. Okay, so the SN1 reaction is also known as the nucleophilic substitution reaction. And basically, the rate determining step involves one component, which is why they call it SN1. And typically it takes place in 2 steps. Okay, so I'll just show these 2 steps now. So the first step is when we have our reactant. So let's say we had a bromine attached to this carbon, this tertiary carbon group. And the first step is the loss of our leaving group, which is bromine. Okay, so after bromine leaves, we get this positively charged carbon group like this called a carbocation. So this brings us to the second step, which is called the nucleophilic attack. So this is when our nucleophile comes in and stabilizes that positive charge or neutralizes it. And our final product now has a chlorine group. So that can be any nucleophile, but I just used chlorine for the example. And the loss of our leaving group is known as the rate determining step. So there are different factors that can tell us when an SN1 reaction may occur. So typically, SN1 reactions occurs with a hindered electrophile. And if there's any potential for resonance stability. So in our case, stability. So in our case, we have a tertiary carbon, which is pretty good at stabilizing this positive charge for the carbocation intermediate. So I'll say for resonance stabilized carbocation. And typically, our nucleophile can be uncharged, and it might take place when we have a protic solvent. Okay, so the junior tutor said that the SN1 reaction is a nucleophilic substitution in which the rate determining step involves one component. They have one nucleophile substitutes the other via the formation of a positively charged intermediate. These reactions take place in 2 steps. In the first step, the leaving group departs with a shared pair of electrons, forming an intermediate, and the attack of the incoming nucleophile takes place in the second step to form a substitution product. Okay, so here's their reaction. They are unimolecular. They give a racemization of stereochemistry at the reaction center. Neighboring group participation in SN1 reactions can be important. So they also have the mechanism, and they break down the 2 steps again. And the rate depends on both the ability of the solvent to keep opposite charges separated and its ability to stabilize both positive and negative sites by solvation. Okay, so this solution is correct. Okay, so question number 7 is to give the IUPAC name for the following compound. So here we have a 6-membered carbon ring that contains a double bond. And we have a 2-carbon chain on this carbon and a 3-carbon chain on the other. So when naming these compounds, we first want to identify our parent. So this is typically the longest carbon chain, or in this case, cyclic ring, with our most important groups. So here you'll notice that we have a double bond in the 6-membered ring. So I can identify my parent as this part of the molecule. So the second step is to number these carbons. And we want to ensure we have the lowest number possible in our final name. So typically when we have only the one double bond, this will tell us that that should be where carbon 1 is, since 1 is the lowest number we can have. So I'm going to start numbering from here. So this is carbon 1, 2, 3, 4, 5, 6. Okay. And the next step is to identify our substituents. So here we have a 2-carbon chain. So this is known as ethyl. And here you'll notice that this chain is 3 carbons long, but instead of it being bonded to the first carbon, it's bonded to the middle carbon. So instead of a propyl group, this is called isopropyl, since it's bonded to this carbon right there. And now we can finally name our compound. So we want to name our substituents first and show which carbon it is on. So we name it in alphabetical order. So first is our ethyl group, and it's on carbon 2. So we say 2-ethyl. And then on carbon 4, we have isopropyl. And then the name of our parent, it's a cyclic structure. So we write cyclo. And the number of carbons in the cycle is 6. So we use the prefix hex. And there's a double bond as well. So it's just going to be cyclohexene. Okay, so that's our final name. So let's see what the junior tutor said. Naming an alkene is like naming an alkane, but instead of the suffix "ane", the suffix used is "ene". Parent chain corresponds to the longest possible chain of the compound bearing the double bond, and the prefix used for the name varies depending on the number of carbon atom comprising this chain. Okay, and they mentioned that you add cyclo before the parent name, and they summarize all the different prefixes that you should put in front of the parent. And then they mentioned how you would name the side groups and showed the parent chain and numbered it and gave 2-ethyl 4-isopropyl cyclohexene. So this solution is correct. Okay, so question number 8 is, what is an example of a decomposition reaction? So when we have a decomposition reaction, this is a reaction that breaks down a reactant to 2 or more products. Okay, so I'll give the general reaction scheme for a decomposition reaction. Let's say we had compound AB. This will break down to A plus B. Okay, so I'll also add some real life examples. So let's say we had zinc carbonate. And if this was exposed to like heat, then it can break down to zinc oxide plus carbon dioxide gas. And another example would be if we had HBr. When exposed to light, this can break down to hydrogen gas plus bromine gas. So these are examples of decomposition reactions. And the junior tutor said that it's defined as a reaction that breaks down a compound into simpler substances. This reaction can be best described in general form. Okay, and an example of decomposition reaction is the decomposition of water into hydrogen and oxygen with the use of electricity. So 2H2O makes 2H2 plus O2. Another example is the decomposition of the salt, sodium chloride, into its corresponding ions. So sodium chloride makes sodium plus chlorine minus. So this solution is correct. Question number 9 is, how many electrons does an atom of sulfur have in its valence shell? So let's locate sulfur on the periodic table. And we can find it here in group 6A. So this tells us that there are 6 valence electrons. And another way of finding out how many valence electrons is by finding out the total number of electrons in sulfur. So sulfur has the atomic number of 16. So this means we have 16 protons and also 16 electrons if we have a neutral sulfur atom. So if we are to sketch out what a sulfur atom might look like, we'll have 2 electrons in the innermost shell. And then the second shell can house 8 electrons. So now I've drawn 10 out of the 16 And then in the final valence shell, we'll have 6 valence electrons left over. And I like that. So the answer is option E. And Junior Tutor said that sulfur is a group 16 or 6A element. Oh, I wrote 4A here. Roman numerals. 6A. Which means it has 6 valence electrons in its valence shell. Yep. So this solution is correct. Okay, so question 10 is a multi-step question. Acetone has a density of 0.786 grams per mils and a heat of combustion of 428 kilocalories per mole. What is the complete equation for the combustion of propanone? How much heat in kilojoules is released if 2.58 grams of propanone reacts with oxygen? How many grams of oxygen gas are needed to react with 15 mils of propanone? And how many liters of carbon dioxide are produced in STP in part C, so standard temperature and pressure. Okay, so let's start off. I believe this is question 10. So 10A is to first write the complete equation for the combustion of propanone. So propanone is a 3-membered carbon chain that contains a ketone group. Oops. I'll just draw it like this. That contains a ketone group in the middle. And it is known as C3H6O. So I'll just label this as propanone. And when we have a combustion reaction, this is reacted with oxygen gas, and the products are water plus carbon dioxide. So when balancing out this equation, we first need to balance out our carbons. So we have 3 carbons on our reactant side, so we need 3 carbons in our product side. So I put a 3 in front of CO2. And next I like to balance out my hydrogens. So we have 6 hydrogens in our reactant side. So I need to put a coefficient of 3 in front of the H2O. And finally, we'll balance out our oxygens. So on our product side, we now have 6 plus CO2. Oh wait, so 3 plus 6, so 9. And we only have 3 on our reactant side. So to make 9 oxygens on our reactant side, if I put a 4 in front of O2, then this should balance out my reaction. So this was part A. And for part B, we want to know how much heat in kilojoules is released if 2.58 grams of propanone reacts with oxygen. So we know the mass of the propanone is 2.58 grams. And we first need to calculate the molar mass of propanone as well. So the molar mass of propanone will be 3 times the molar mass of carbon. plus 6 times the molar mass of hydrogen plus the molar mass of oxygen. So these values are just found on your periodic table. So for carbon, it's 12.01 grams per mole. Hydrogen's is 1.01 grams per mole. And oxygen's is around 16. And you should end up with a molar mass of 58 grams per mole. Okay, so we have our mass and our molar mass. And the next part is to calculate the number of moles. So number of moles is equal to mass divided by molar mass. So we just need to plug in our values. 2.58 grams divided by 58 grams per mole gives us 0.44 moles of propanone. So to calculate heat, we know that the heat of combustion is 428 kilocalories per mole. So since we're given the number of moles, all we need to do is multiply these two values. So I can say that heat is equal to 428 kilocalories per mole. And we just need to multiply this by our number of moles. And the moles will cancel out. And we get heat equal to 19.04 kilocalories. And the answer wants us to give it in kilojoules, or the question wants us to give it in kilojoules. So we just need to multiply by the conversion factor, which is 4.184 kilojoules per kilocal. And our final answer is 79.66 kilojoules. Okay, so that was part B. Part C asks how many grams of oxygen gas are needed to react with 15 milliliters of propanone. So if we recall the density equation, which I'll write up here, density is equal to mass over volume. So if we rearrange this equation, then we can solve for the mass of propanone that reacts with oxygen gas. So I'll just write here that mass is equal to density times volume. So the density was given in the equation. It was 0.786 grams per milliliter. And our volume of propanone was 15 milliliters. So now our milliliters will cancel out, and we know our mass of propanone now, which is 11.79 grams. So now that we have our grams of propanone, we need to calculate its number of moles. So again, number of moles is equal to mass over molar mass. So our mass is 11.79 grams. Our molar mass we found in the previous question. It's 58 grams per mole. And we get 0.2 moles of propanone. So from here, we can use molar ratios to find the moles of oxygen gas that reacts with 0.2 moles of propanone. So by using our balanced equation that we found in the first question, we can multiply this by the molar ratio. So we know that 4 moles of oxygen is needed to react with 1 mole of propanone. So if we multiply 0.2 by 4, then we get around 0.8 moles of O2. And finally, we can calculate the mass of O2 by multiplying these number of moles by O2's molar mass. So 0.8 moles of O2, and the molar mass of O2 is 32 grams per mole. So then we get, let me calculate this here. 0.8 times 32, around 25.6 grams of oxygen. Let me circle our answers. This was the answer for part 2. And now we can answer part D, which is how many liters of carbon dioxide are produced in a standard temperature and pressure in part C. So again, we know we have 0.2 moles of propanone, and we can multiply by the molar ratio of carbon dioxide and the propanone to get the number of moles of carbon dioxide. So 3 moles of CO2 reacts with 1 mole of propanone, and we also want to take into account the molar volume of a gas at standard temperature and pressure, which is 22.4 liters. So we multiply this whole thing by 22.4 liters, which I'll put in brackets, is molar volume at STP. And our final answer would then be 13.7 liters of CO2. Okay, so again, this was a multi-step question, and it's a good question to ask on like a midterm or an exam because it touches upon so many different topics. So for part A, they balance the equation. So 1 propanone plus 4 O2 makes 3 CO2 plus 3 water. The mass of the sample is 2.58. They converted to kilojoules first, which is also what you can do for this question. And they found the molar mass to be 58 grams per mole. And they also got 79.5 kilojoules of heat. For part C, they have the volume of the sample, the molar mass, and the density. But here they said that the molar mass of oxygen is 16 grams per mole. So they used 16 instead of 32, and they got 13 grams of O2. So it's pretty much the same as ours, except divided by 2. So I'm just going to take note that they could also use the molar mass of oxygen gas, which was O2. But the approach is still correct. And then in part D, they wrote down what was given, and they summed up how to find the number of moles of propanone again, divided it by 58.1, and then multiplied it by 3, and then they plugged it into the ideal gas law. So this gives the same answer, which is 13.6 or 7. So that part is still correct. So this solution is correct. Great job. However, okay, the approach for part C was also correct. However, the molar mass can be for O2, which is 32 grams per mole, giving a final answer of 25.6 grams of O2 instead of 13 grams. Yep, so they just multiplied by a single atom of oxygen, which was 16 grams per mole. But if you wanted to do diatomic oxygen, you multiply by 32 grams per mole. Okay, but this solution is still correct. Okay, so those are all the questions for this session. And if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. If you'd like to submit a question of your own, then check out the links in the description. Also, if you enjoyed today's video, you can give it a thumbs up and a comment, or you can share with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.